Welcome to today's webinar. Today we will show you the import and the design of an advanced steel model in RFEM 6. My name is Andreas Hörold. I'm responsible for marketing and public relations in the company Dlubal Software. For instance, the German and English webinars, technical content of the website, and so on. I will be the moderator today, and I will answer your questions together with Paul Sievergien. My colleague Lukas Süle will be the presenter today. Lukas and Paul are the main responsible persons for the development of the interfaces in our software, and both of them are working in the customer support team. You can ask questions when you press the button with the question mark, then enter your question in that field, present, and we will receive your question and we will answer you. The other way is to watch the entire webinar and then email your questions to info@dlubal.com. Okay, that's for the moment all from my side. I hand over to Lukas. Lukas, it's your turn.
Andreas, thank you very much for the introduction. I want to continue with the content of today's webinar. I will begin with the, let's say, export from Advanced Steel to RFEM 6. Here I will focus on the SDNF format. Then I will import this structure in RFEM 6 and design it with the Steel Design add-on. And at the end, I will export my RFEM structure into Advanced Steel. Let's start directly. I want to show you the Advanced Steel model that I prepared for today's webinar. It's a little steel construction, as you can see. The Advanced Steel user already modeled the beams. He modeled some connections. It's mainly I sections here, HEA sections, IPE sections. So nothing too specific. And the idea is that there is already a model in Advanced Steel or any other, let's say, detailing software. And the person wants to share this information, this model with the structural engineer, so he doesn't have to start from scratch. Yeah, that is the idea. And there are now multiple ways how you can share his information with the structural engineer. One way would obviously be the IFC format. Yeah, that's always possible. So the Advanced Steel user exports it into IFC, then the structural engineer will import the IFC. He will convert the IFC objects into members. He has to connect them using, for example, the regular rule-based link generator, and then he can design it. That workflow I showed in a previous webinar. Today I want to focus on the exchange via the SDNF format. The SDNF format allows us to export the beams, columns, so members in general, but it also allows us to export plates. So plates like here that are used here in this tapering, in this connection, or here as stiffeners and so on. The question is, do I really need the plates in RFEM 6? And if I think a couple steps forward, I import this data into RFEM 6. I want to do a analysis on a beam model, then those plates won't help me at all. Yeah, there's no benefit in having a surface here in that area. Therefore, I will not export any of the plates. I'm only interested in the beams. So to reduce this structure, that it shows me only the beams, I can use, for example, the model browser. For example, sort by cross sections, and then just select all the beams with the cross sections that I'm interested in. And then we have a couple down here, I think. Yeah, those ones here, the diagonals, and then isolate them. Okay, so now all the connection details are hidden. Yeah, I can only my beams are visible, the ones that I want to export. Now I can select the structure and I can go to export and import and say export SDNF file. Let me put it on my desktop. Advanced Steel model tests. I don't know, anything. And then the SDNF version 3. Here I can choose that I want to select only the selected model or the whole model. So I'm going for the selection only and press OK. The export is running, as you can see on the bottom right. And now it's done. And now I can go into RFEM 6 and run the import. Quite straightforward. File, import, SDNF. That is my file. And it will always take a couple seconds. All right. The first thing that I will do is I will mirror the coordinates. I will mirror the Y and the Z coordinate, simply because we are usually going with global Z downward in RFEM 6, and in Advanced Steel, global Z axis is upward, so everything is mirrored. So to have my structure not upside down after the import, I mirror it in advance. And then I can control here what should be imported, and I go for everything, kind of. Click OK. And now I have to deal with the cross-section and material conversion. Yeah, you can imagine that materials, but also cross-sections are named differently in other programs compared to RFEM 6. What will happen is the following. You will get these tables, and if you do it for the first time, only the left side will be filled with the names from the external materials, yeah, and the external cross-sections. So this is imported from Advanced Steel, and the right side will be empty most likely. So your job would be to assign a proper RFEM cross-section to the imported section name. Yeah. So you can go for IPEs according to Eurocode or IPE according to any other code. So you have to be more specific here. Anyhow, you do it only once. Yeah, those section names will be saved. So when you do it the second time, you just click OK, as I do it here. Yeah, I did it in advance. So the import is running now, and there is my imported file. All right. Overall, I think it looks similar to the Advanced Steel model. Now we have all the beams and diagonals. And yeah, what are the first things that I do after an import? First of all, what I directly notice is if we take a look at the wireframe model, then we can see there are many eccentricities assigned to our members. So if I show the rendering, it looks really nice. We even have a little gap in here between the beam and the column, and this is coming from the physical model from Advanced Steel, yeah, because we have here an end plate in between, and on the bottom there was this tapering. This is what the eccentricities are coming from. Let me show the Advanced Steel model again. Yeah, so what we are exporting from Advanced Steel into the SDNF format is related to the red lines that we can see here. Yeah, these are the, I don't know, baselines of the members, let's say. I'm not sure if that's the official name in Advanced Steel, but it's the baseline of these members, and they are all connected here, as you can see. Yeah? The physical model in Advanced Steel, however, is not intersecting. Yeah, the beams are ending where they should end, depending on which joint you assign here. So the SDNF format contains the coordinates of the baselines, and then the eccentricities are simply the result of the eccentric location of the beam compared to the baseline. Same here on this first floor, yeah, baseline on the top flange, and then the eccentricity vertically and slightly horizontally due to the joint. Now, if we think about it, going back into RFEM 6, I actually don't want to have the eccentricity in my model. Why is maybe the question. Well, imagine you have an axial force in this beam here, it would lead to additional bending moments in the column because of the eccentricity. Yeah? Axial force multiplied by the lever arm. In reality, this eccentricity, there is no such eccentricity. Yeah? There are no additional bending moments in this area. So it doesn't make sense to use the eccentricities here. So therefore, I will go to types of members and remove all the eccentricities. Now, if you're 100% correct, or if you want to be 100% correct, you would now say, okay, but now the beams are on a higher level compared to the physical model in Advanced Steel. So what you obviously can do is you can always go to these coordinates and change it to the appropriate level or appropriate height. You can modify that. For the sake of the webinar here, I will just skip this little adaptation in the model. Okay, that's the first thing. Then what else am I usually checking? Well, we have in RFEM 6 a lot of model checking features. You can find them in the tool menu, model check, and here you can check for identical nodes. Here nothing will be found. There are 0 groups. That means there are no identical nodes. It's, however, a good check to run. Identical nodes doesn't mean they are 100% lying on top of each other. There could be even a small distance in between. And let's say there are 2 nodes that have a distance of 1 millimeter. Usually that is a modeling error. That's not supposed to happen. Yeah, and this would be shown via this check, and then you can directly see where maybe members are not really connected. Another check could be overlapping lines or members. No overlapping members were found here. What is this check good for? Well, assume you have multiple members on the same location in Advanced Steel. Maybe you don't see that directly. I don't know how Advanced Steel shows that, if there are 2 members with the same section in the same place, if there's also model check or not. But if you would export that and you get double members in RFEM, then yeah, that's not ideal. So overlapping lines and members will check for that. And the last one that I'm running here is crossing or unconnected lines and members. And this will show us some, I don't want to call it issues, but some locations. And you click on each group individually. You can see, for example, doesn't matter, this member and this member. Yeah, they are both highlighted now. And this is like a crossing unconnected member. And that simply means that this member is going from this node to this node, and this member is lying with its end node on this member. But since this member is not divided, it simply shows us this. Yeah, it shows, hey, there's an undivided member where another member is placed on top of it. And while for the static analysis, this is not a big issue. If I run an analysis now, these members will be connected. In our Steel design or other design add-ons, this is not ideal, let's say. So if you have such a model where there's a beam connecting to another beam, you have 2 options usually. You can either connect lines and members, so you really split them up. Let me do it once. Yeah. Now this member ends here, this member ends here, so they share the same node and they are fully connected. That's one option. The other option would be to leave this member over the full length, but use another type of node instead. So instead of these red nodes, we could use nodes with the type on member. So let me do this change. I select all of the nodes except the nodes on top of my columns, because those are real end nodes, and this one. And now I can modify all the other selected nodes by simply double-clicking on them and say here on member. So after this modification, you can see the color switch to blue. And now this is a proper definition of 2 members connecting each other. Yeah. This member here has now an information about those nodes lying on top of them or on them. You can also see it if you open the Edit Member dialog. You have now a tab, Nodes on Member, and they are all listed here. And this is this is a better way to model it. Okay. so far regarding that. Last thing that we could check is maybe cross-sections and materials in general. Yeah, it's always good that we know the conversion worked properly. So I can go into my display navigator, into colors of rendered objects by object property, and then, for example, cross sections. Yeah, so all my cross sections will be rendered in different colors. And with this information from the panel, you can quickly control if the right sections were assigned. Same for the materials here, everything is S355. Yeah, and so on. So those are the checks that I recommend in general after importing any kind of data. It helps to prevent issues. Let's continue. What else do I have to do? I have to support the structure. I have to apply some loads, obviously, and then we can slightly think about the analysis and design. So regarding the support, I will simply use nodal supports on the bottom here. 4 nodes. Okay, we can increase the size a bit so it's more visible. And the next thing that I have to think about is the analytical model. Yeah, the connections of the beams. Currently, every beam is modeled or imported as a beam type. So every internal force, every bending moment will be transferred to any other member. That means a bending My in that beam will be a torsion in this member. This is not ideal. Therefore, I want to assign some hinges. And since many of the beams are typical truss members, so they have a hinge for bending moments at the start and at the end, I can use a specific member type. So let me select all of the members. I'm thinking what would be the fastest way. Let's just do it graphically. So I select all these diagonals and all these crossing members in these levels, and then additionally also these members here. Yeah. So in that area we had rigid frames, and in the other direction there were only let's say hinged connections. So I selected all the members that I want to modify. I double click here, and then my member dialog should open. Yeah, right. And I will change it from beam, where every internal force will be transferred, to truss member. And then the graphic should update. So here only axial and shear forces will be transferred from this beam to the next beam. All right, let's graphically check it. Yeah, so rigid beams, rigid frames in this direction, hinged in this. Okay. So far, so good. Let's before we, let's say, apply more loads and all these kind of things, we could run a simple static analysis. There's always the load case, the dead load case, active by default. We can simply run the analysis of that load case to see if the structure is fine, if it behaves according to our expectations, or if there's maybe an instability. So before we deal with the loading, we make sure the model itself is okay. We get deformations, so we get the results in general. We get the axial forces, bending moments. Let's have a brief look. And the bending moments also look fine. Yeah, we have single span beam, like bending moment in all of the truss beams. And for our rigid frame, we have, let's say the right bending moments. Yeah. So general behavior of the file is fine. All right, then let's continue with the loads and load combinations. Before we apply any load, we should check if the right codes are assigned. Yeah, this file was created via an import, so I haven't even thought about the standards and national annexes here. So let's check that for the load cases and classifications. I want to use the Eurocode and let's say German national annex. And for load wizards, so let's assume we want to apply some snow or wind loads, I also want to use the German national annex. So the right snow and wind zone cards pop up. Okay, that is that. now we can create some load cases. Actually, I want to keep it very simple. We have the dead load case here as default. And I want to create exactly one more for the live loads. Maybe storage areas. And then I can assign a load to it. And I will simply place a surface load on top of this and this level. There are many webinars that show various loads. In my case, I want to keep it quite simple today. So I'm using the member load from area load generator. So I can easily say, okay, I want to have 5 kilonewton per square meter in that area here. Let me select the nodes. So from here to here, to here to here. So I left a little area open. There's a stairway, I think, from the bottom to this floor. So there's an opening basically. So this is the first load. And then I create another one on the top of the structure, 3 kilonewton per square meter, same load case. And here I simply select the full plane. Okay. Those are my loads. I can also show them separately. As you know, it will also show the areas from the surface load. So you can see how the surface load will be spread to the members by these red, black lines here. Yeah. Distribution areas, that was the name. Yeah. Okay. So those are my loads. Now, let's combine the load cases. We can do that either manually. I can manually say, okay, I want to have a design situation, permanent and transient. And then here, manually create my load cases. Or if we activate the combination wizard, it will be done automatically. Concerning the combinations, I'm only interested in the ultimate limit state for today. And then it will combine them automatically. Now let's have a first thought about the structure stability. So before we even do any of the steel design checks, we can check the general stability of the structure by calculating the critical load factor. And to do so, I need a specific add-on, which I will activate now. It's called structure stability. This add-on, as I said, will calculate the critical load factor. It will calculate the eigenforms, the buckling length of the members, and so on. And I can control it, for example, within this combination wizard. So I can go to my design situation, ultimate limit state, and then I have different rule sets how my load cases should be combined. And I have here an option that it should be combined linear or according to second order, or can even modify that rule set. And I want to have in the beginning a setting in a way that the load combinations will be calculated geometrically linear, but additionally stability analysis should run. For example, 40 eigenvalues should be calculated. So by assigning this setting to my combination wizard, all my load combinations, which are only 2 here, will have the setting activated, calculate critical load. So that is so far okay. We can run the analysis. We can see it will calculate this static analysis of my load cases and combinations, and then it will run the stability analysis. All right. Now, there are rules in the Eurocode that when the critical load factor is smaller than 10 for an elastic analysis, or 15 for a plastic analysis, or elastic plastic design, then you have to use a second order analysis for the load combinations. If the critical load factor is higher than 10 or 15, you can actually use a linear analysis. And now the question is, what is the smallest critical load factor in this structure? And for us, it's quite simple. We have 2 combinations that we can check manually, but imagine there would be hundreds of load combinations. then you can go into the static analysis, into the design situation here, and you can see the minimum critical load factor of 2.3 is coming or is resulting from combination number 2. So we can have a look at combination number 2 results and also the stability analysis results. And we can, for example, display the mode shapes. And for a better rendering, I will display them as colored sections. So first information that we get from here is the critical load factor is below 10. So we definitely have to run a second order analysis. The axial forces and will cause or will have a huge effect on the bending moments because the beams are so slender, basically. So let's have a look at the shapes. I can go through each critical load factor here. This is all local buckling of my diagonals. And then still with a very small critical load factor, I have a global stability issue, as you can see here. It's an asymmetric buckling of my columns. And if I check the following critical load factor, it's symmetric buckling of my structure. So the columns will all fail in this direction. And I think it's kind of logical, because in the upper floor we have, as I said, a rigid frame in this direction, but in this direction everything is connected via hinges. So no bending moments transfer. So it's really not very stable. For this floor it's okay because of the diagonals. Here we do not have them. So to optimize my structure regarding stability, I would simply say or decide we definitely need also these diagonals from the bottom floor and the upper floor. I copied them using drag and drop. Drag and drop, just select the objects you want, keep Control pressed, and then move it wherever you need them. And then they will be copied. Let's not forget about the red and the blue nodes. I have red nodes here now, but again, I can simply change them to on members, and then they are properly connected to the other beams. All right. That is my first, let's say, modification of the structure. I optimized them. I try to deal with the global stability issues. So let's run the analysis again. Static analysis and stability analysis. Okay. Now let's have again a look at the critical load factor. It's still small, 2.3, but this is still local buckling of the diagonals. I assume at least. Let's see. Now let's have a look at the eigenmodes again. So still local buckling, obviously. I didn't change anything in that regard. But if we go now through the mode shapes, there is no mode shape that shows the global stability issue. It's all local buckling. Let's continue. Maybe another shape will show up or not. Here's the first, let's say, it's still a local buckling shape of the column, but it's the critical load factor of 20. So this is maybe not that serious. Anyhow, we can nicely see that buckling of columns in that direction will be sinus shape-like. So it's not buckling over the whole length. It's like a sinus curve. All right, so my global stability issue, I think I controlled or optimized at least. And now we can really think about the steel design of the beams according to Eurocode 3.1.1. How do we check that? So first of all, we need the steel design add-on. This is what we need for designing steel beams according to EC3. Again, let's select the national annex, and that's the first thing that I have to do. didn't know where the support is coming from. Let's remove that. Now we just noticed that we have to run a second order analysis, right? The critical load factor was below 10. So let's modify my combinations again. Instead of running using a rule set that combines load cases according to first order, or that creates load combinations that will be calculated according to first order, I will switch it to the second order rule set. So my load combinations will be analyzed according to second order analysis. My stability analysis is also turned off. I don't need it anymore right now. So these load combinations are now calculated according to second order analysis. Now, before we start with assigning buckling lengths and so on, we have to think about which rule or we are using for the steel design. The Eurocode gives us here different possibilities, and if you have the Eurocode open by any chance, in chapter 5.2.2 in bracket 7, there are multiple, well, actually three different variants, and I summed them up in my PowerPoint here. So let me briefly show it. So there are different methods. Yeah, again, Eurocode 3-1-1, 5.2.2 in bracket 7. There's method A, which is basically stating that if you consider the global and the local imperfections in your static analysis and you run a second order analysis, then there is no need to run any stability check according to chapter 6.3. You can simply run a cross-section check, and if the cross-section check is fulfilled, then also your stability issue or the stability is checked by that. Yeah. So the thing is that the difference is that we bring all the stability facts into the static analysis by using imperfections, second order analysis, and so on. So if the cross-section check is fulfilled, we also checked the stability. In that specific case here in my picture, I have the inclination of my columns as global imperfection, the precamber of my columns for the local imperfections. And again, second order analysis, cross-section checks means if the cross-section check is fulfilled, the buckling of my column in the plane would be fulfilled. Yeah, I don't even need to check buckling. I still have to check buckling out of plane, and I still have to check lateral torsional buckling, but this picture itself describes buckling in plane via cross-section check. There's another method described under B. It's, let's say, a reduced analysis compared to A. You still apply the global imperfections. You still run a second order analysis. But now you have to run a stability check according to chapter 6.3. The difference is that the buckling length for the beams simply is the length of the member. Yeah, you don't have to calculate, let's say, a little bit more complicated beta value. You can simply say buckling length equals member length. And then there's a third method under 5.2.2 in brackets 8. And this is basically the design according to a first order analysis without any imperfections. But here you have to run the stability checks according to chapter 6.3, and you have to calculate this buckling length, the beta value, which is then a little bit more complicated. From my work here in the support, most of the customers use method B, I would say. Method B and A. C is really not that common in my opinion. So we also aim for method B. So let's go back into RFEM 5. And for method B, I need a second order analysis, which I just assigned before. I need the global imperfections, so the inclination of my columns here. And that can be done with the imperfection cases. So I create two imperfection cases here. Imp in, say, start with X plus X, maybe. And I make a copy in plus Y. All right. So these are like load cases just for imperfections, and then I have to fill these imperfection cases with imperfections itself. And it can be done in various ways. There's the imperfection load for members. And here I can simply say I want an initial sway based on the Eurocode 3. So I have a base value of 1 divided by 200. You can always use that. But if you want to be a little bit more economical, you can assign as well the structure height here, maybe the amount of columns in the same row, and it will increase, which kind of means decrease the initial sway of the structure, simply because it's quite uncommon that all of the beams in one row will have the same inclination in reality. Every column probably will be measured by itself, and it's not that common that you have an inclination for all of them at the same time. So, and I can assign this initial sway to my columns. I simply select them, and let me change something. The imperfection direction is minus z. Minus z will be plus x, as I hopefully intended. So now all of my 4 columns have this global inclination in plus x direction. Same I will do for the imperfection case in y. We do it rather quickly now. Initial sway, EC3 minus y, same values. All right. In plus y direction now. It depends. It's of course not really perfectly symmetrical, this whole structure. So you can also think about minus y and minus x. I skipped that here for the webinar. All right. So I have my imperfection cases. Now, obviously, I need to consider these imperfections in my load combinations. This is, however, already included in my combination rule. So I have now 4 load combinations, and every time the imperfection switches. So load case 1 with imperfection x, load case 2 with imperfection, load case 1 with imperfection 2, and same for the other 2 combinations. All right. And now the last thing that I have to do is I have to assign my stability related information or properties to my beams. And let's start with the columns. There are, again, different design checks that we can use. In my case, I want to use the equivalent member method kind of. So I can, for example, modify or edit a member, go into the design type tab, and here you can assign effective length types, basically. So I create one of these types. All these stability issues should be checked: buckling, torsional buckling, lateral torsional buckling. And then I have to deal with the settings in here. Let me close this dialog one more time because I want to show the structure at the same time. So I move this a little bit to the side, and like this and this. And now I have to define basically how this column is supported for the internal eigenvalue method for the determination of MCR, which we need for the lateral torsional buckling check. So the default setting is that we have a fork supported beam. So a support at the start and at the end of the column in this case. We don't automatically detect any additional supports. So if you want to consider them, you can select simply the beam itself, and it will tell you, hey, there is an additional intermediate node. And how should this one be supported? Well, in both local Y and local Z direction. So for buckling in Y, we have support by this crossing beam, and in buckling about X, in X direction, we have the support of this beam. This is what I'm defining here. And then I will get segmented, like 2 segments for my beam. And for each segment, I can decide what is the buckling length. In my case, I simply say buckling length factor is equaling to 1. So buckling length is equal to member length or segment length. All right, then I can press OK, or maybe even assign this type that I just created to all of my columns. Yeah, I forgot that I did it only for one column. I can say this is the same logic that we use on all of the columns. And now let's double check that the support that I defined is on the right location. We can do this again in the display navigator, and we can say here, please show me the effective length supports basically. And we can see that it's directly, the support is there where I have the crossing beams. Yeah, so that's nice to check it graphically. So this is how these are the necessary settings for the columns. Now we can continue with other beams. And one really common case here are these truss members. Yeah, there's like single supported, like fork supported beams at the start and at the end with no intermediate supports. So I will create one more type for that. We can also call it, I don't know, single span beam, or however you want to name this type. And it's basically, yeah, fork supported on both sides, and member length equals buckling length. And I can assign this type to many of the beams here in my example, all of the diagonals, obviously. And then I will select also all these beams, and I will explain it in a second. And also these two main beams here. Okay. So what is my idea behind that? Well, I think it's easy to understand for these diagonal beams, and maybe also for this one here and this one and so on. But now we could argue about this beam here, this crossing beam. It is, of course, supported on both ends, but maybe there's an additional horizontal support by these crossing beams, in these inner smaller crossing beams. And my idea is, let me first check it as single span beam. If the stability, if the design ratio for my stability check is not okay here, if it's above 1, then I can still think about assigning additional horizontal supports. If it is okay, then maybe I can live with that. Yeah, maybe it's conservative. I'm on the safe side. Maybe not that economical. Well, it depends if that's necessary or not. All right, and then I have a couple more beams that I have no settings so far. For example, this one here, there's definitely a vertical support on that node. Same here and on other locations as well. So I need one, or actually two more of these types, and I will start with this one here. I will do it inside the member one more time. So I'm creating one more equivalent member length method. I will import the amount of intermediate nodes via this button, as I showed it in the beginning. And well, here it's visible on the second node, there is a vertical support. So I select that, and I again do not consider any of the additional horizontal supports or crossing beams. Yeah, just vertical one here for now. Let me show if it is assigned correctly. I will show only one member, not all of them. And we can again see, yeah, it's supported on the right node. And now I will assign this type to other beams as well. So, oh, actually, sorry, my bad. The type itself. So this beam here on this, it's always the second node. This beam is supported not on the second node, on the third. I need a different setup for this one. Here it's the second node again. It's also the second one. Sorry, I will change the rendering so it's more obvious. So this one as well. And it's the third one, as I said before. And here it's the second one. Okay. So we have this one here. How do we call it? You said in a second. I don't know. Because of the second node. Let me press OK and show maybe again the supports. So this one here and this one here, just graphically checking if it's on the right location. Yes. Here not yet, because I didn't assign anything here yet. So for this beam and one other beam, I need another type. So design type. Let me import the amount of nodes. And here it's on the third intermediate node where I have the vertical support. Okay. Okay. Let me show the beam again. So now it's on the right location. And I think this member was also missing. I can assign this fourth method to it. Let's rename it so it's kind of logical. Third. Okay. All right, now I should have assigned a stability related property to all of the beams. Yeah, I assigned all of the buckling lengths and settings, and now I can run the steel design. Will take a little second. All right. So this is the result. Let me change the rendering a bit again. Like this. Yeah, there are now different options how we can show these results. Maybe like this. Yeah, so we can see there are a couple of design checks getting closer to design ratio of 1. Here, 85%. But still everything is fulfilled. So there's no need for me to consider the additional crossing beams in my stability analysis. It is okay as it is. We can also check the details of the analysis here in the tables. For example, design ratio by members. And if I select the member here in the graphic, it will directly jump to the member in the table. I can double click here on the results and I get my intermediate results. So I can definitely calculate it by hand and with the help of the formulas for sure. So that's really a nice way to document the results. Okay. So far regarding this steel design. Now there are additional add-ons that would help us to design the steel joints. Not help, they will design the steel joints. But this is not on my, this is, I can't do it today. It will take too much time. So I will stop here. I will also not create a protocol, which is definitely included in RFEM 6. This has been shown in various webinars before. I want to show now also the export from RFEM 6 into Advanced Steel. So this is like a second use case. Let's assume you're a structural engineer. You have this project on your table. You calculated it, you designed it, and now the Advanced Steel user should create the drawings and all these things. Then you can help him by sharing this project or this structure with him via the SDNF format. Obviously, IFC would also be supported. So let's check the options that we have. We can export it here, for example, in the IFC format or in the SDNF format. I don't know exactly how well Advanced Steel can work with IFC files. If they can also convert IFC objects back into native objects. I didn't test that. But what I can say for sure is that the SDNF format is really a really good option. And I will show it in a second. So I will export this structure into an SDNF file. Just name it test, doesn't matter. Again, I will mirror it for the export, so it will show up. It will not show up upside down in Advanced Steel, and everything should be exported. Let's again wait a little second. Export is running. Okay, completed. And now I can go back into Advanced Steel. I will close this file here, the structure. I will create a new one. Okay, and then I can go into the menu Export and Import. I can switch here to Import SDNF. I can select my little test file that I just created. I don't know, general. Select an application. And now he will import the objects. I can choose my insertion point. Let me put it close to the origin. And now that will show up for the first time. When you import it one more time, it will not show up anymore. It's basically similar to what we had in RFEM 6. Yeah, you have to assign a proper Advanced Steel section to the sections that we are importing from RFEM 6. So here I have an HEA 200 from RFEM 6, and I have to assign here the Advanced Steel section to it. So HEA 200, okay. I have to do it a couple of times now. I'm sorry for that, but it hopefully won't take too long. IPE. Oh, HEA, sorry, my bad. HEA 140. Okay. May have a couple of sections, but not too many. IPE 400. Okay. 140. Okay. HEA 240. And that is this hollow core section or pipe section. Hope I can find them quickly. Steel tubes, probably. Oh no. How are they called in here? Round bars, rectangular, hollow. This is rectangular. Sorry. Circular hollow sections. Yeah, right. Yeah, maybe this one here. And let's see if we find this proper section. 101. Oh, it's not the right list. There's another list somewhere. I found it in the German version of Advanced Steel. I will just assign another one now. Yeah, it's not that important here. So we assign all the sections, and now it's IPE. So there's still one more. I sections. I thought this was already the end of the list. Finally. Okay, so these are now the imported data. Again, we have to assign this section once, then he will save it in an internal mapping list. And if I import it one more time, we will get the structure directly. So now let's show it in a shaded rendering. It looks quite good, yeah. It's similar to what we have in RFEM 6. And I can also show that that it is quite usable in Advanced Steel. So what do we get? We get also the center lines that we had before, yeah, these base lines, or how I called them, the red lines. But now it is not eccentric, yeah. So after the import, but I can quickly change it. I can simply select all these beams, go in the advanced properties, and I can say here, for example, yeah, please position it on the top flange. Same here. Advanced properties, positioning top flange. And then it's already in the right location. And I can also use it to assign connections here. So this is real native data that can be used with all the tools that we have. And for example, I can create here I don't know, these little connections between the crossing beams. So this beam and this beam. Then I should get a little dialog, yeah, clip angle. Let me not modify it too much. Looks strange here, I have to say. Was better in the German version. Maybe that's not ideal. I don't know why it's different. Maybe let's try something else. What do we have in knee joint? So I need to select the column and the beam with the plate haunch. This looks much better now. I can modify the distances somewhere here. I think, I don't know, 12 millimeters for the horizontal distances. I can change the bolts here. Let's say I have 3 group of bolts with a distance of 135, and then an additional row, which is then, that's too far, somewhere here, and then I have a nice joint. Yeah, just the stiffener here is on the wrong side, which I can easily mirror, and I can also say, please assign this joint on other locations, and then we quickly generate connections in here. So I can use these imported beams directly in these, let's say, advanced tools. Yeah. So this would definitely be a help for the advanced steel user, I would say. And yeah, this then is also the end of my part for today's webinar. I hope I was able to show some nice features, share some thoughts, and I will thank you. I'm thanking you for the attendance, and I hand it back to you, Andreas.
Thank you, Lucas, for your presentation. At the end of the webinar, I have additional hints for you. For example, to our online courses, there's the RFEM 6 course. It's a course for beginners. The UCode 2 course for the concrete design. The UCode 3 course for the steel design. The UCode 5 course for the timber design. The UCode 8 course for the earthquake design with RFEM 6. And the AI masterclass course for the use of artificial intelligence. For more information and prices, just scan the QR codes or click at the links here. You can get an RFEM 6 course or an Eurocode course for free when you submit your customer project, and when we publish it, you can scan the QR code or click at the link here, and you will reach a form where you can upload all your files. That is not much work for you. Yeah, an additional hint to our free online services. There's the Dlubal community. You can ask questions there, and our support team or other community members will answer you. There's the GeoZone tool for the determination of wind, snow, and the earthquake loads. You can download 3D models, this template for your project, for example. And you can download the free trial versions of RFEM 6, RSTAP 9, RWind 3, and RSection. You can find more information on our website, dlubal.com, for example, the recorded webinars, the knowledge base articles. You can ask the AI assistant Mia 24/7, all the time. Okay, that should be also all from my side. I thank you for your attention. Thanks again to Lucas for your presentation. Thanks to Paul for the support by answering the questions. I wish you all a nice rest of the day. I hope we meet each other in a future webinar. See you then. Bye-bye.